let us discuss Green's theorem in a plane. Green's theorem, which relates the line integral and the surface integral. So line integral can be converted into surface integral, and surface integral can be converted into line integral. The statement goes like this. Let S be a closed surface in a plane enclosed by a curve C, then if M and M are continuous and differentiable scalar functions of x and y in S, then the single integral over contour surface, contour m dx plus n dy, which is equal to double integral surface integral dn by dx minus dm by dy times dx dy. So this is statement. The surface integral can be converted into line integral, and line integral can be converted into surface integral. And the figure, the description for the figure goes like this. So we have a surface which is enclosed by a curve C, and there are two lines x equals a and b which are parallel to y axis, and they intersect a and b. So these two lines, they are parallel to y axis and they intersect a and b. And another two lines, y equal to c and y equal to d, they are parallel to x axis and they intersect d and e. So we have now two curves connecting a, e, b, and another curve is b, d, a. AEB denotes C1 curve, which is a function of f of x, and BDA is C2 curve, which is g of x, and of course the complete curve, which is equal to C1 plus C2. So the description goes like this. And here f of x is less than or equal to g of x. Now let us consider, in the Green's theorem, let us consider the right hand side, the first term. The first term is partial dm by dy dx dy. So we have now two limits. One goes from, for x, goes from a to b. Then another one is f to g. So dm by dy dx. And after integrating with respect to dy, that will give us m is a function of x comma y, and the upper limit is g and lower limit is f dx. Now we can substitute for the upper limit for y, which is nothing but g. So we have m of x comma g minus m is a function of x comma f. But here the first integral with the curve C2, which is g of x. Look at the graph. The first integral is nothing but g of x. It starts from b to a, doesn't start from a to b. See, the curve is like this. So it starts from b to a. Hence, we are going to interchange the limit. So b to a. Instead of a to b, we are going to change the limit as b to a. The first integral is related with the curve C2, which is g of x. When the limit goes from b to a, thus the first integral with a change in limit becomes minus b to a integral b to a m of x comma g minus integral a to b m is a function of x comma f dx. So this can be written as, instead of g we can write this as y, and this is for the first one, this is for the curve C2, and this is for C1. And C1 plus C2 equal to C, we know already. So this is totally we can write as minus integral m is a function of x comma y dx. So left hand side is already double integral dm by dy dx dy. So which is equal to m dx. So with a minus sign. Similarly, for the right hand side also we can obtain double integral surface integral dm by dx dx dy, which is equal to single integral n dy. Now adding 3 and 4. Just add 3 and 4 completely will give us this equation. And of course, this can be written as single integral m dx plus n dy, which is equal to surface integral partial dn by dx minus dm by dy dx dy. So this is nothing but Green's theorem. Using Green's theorem, let us evaluate single integral, contour integral x squared y dx plus x squared dy, where C is the boundary describing y equal to x in a counter clockwise of a triangle with 0, 0, 1, 0, 1, 1. So the figure is described as like this. So we have the origin, and in the x-axis we have 1, 0, and we have with a line y equal to x, and this coordinate will be 1, 1. Using Green's theorem in a plane, we have this statement, and we know that m dx plus n dy, which is given as x squared y dx plus x squared dy. So comparing the same coefficients, we have m dx equal to x squared y dx. So m is nothing but x squared y. Differentiating with respect to y, that will give us dm by dy, which is equal to x squared. Similarly, n dy equal to x squared dy, and n equals x squared. Differentiating n with respect to x will give us 2x. Now we can substitute. So this is given us. We will have to evaluate x squared y dx plus x squared dy, and we can, here it is given as dm by dy is nothing but x squared, dn by dx nothing but 2x. So this is 2x and this is x squared. So we have 2x minus x squared dx dy. And of course limits will be 0 to n for x and for y. And we know that the straight line equation is given as y equal to x. So y has a limit 0 to x. Now integrating this integral, so we have now y and the limit will be 0 to x. So substituting the limit, that will give us x. Now multiplying with the x, 2x minus x squared, we will have 2x squared minus x cube. Now integrate with respect to x, that will give us 2x cube by 3 minus x to the power 4 by 4 with a limit 0 to 1. So I have written the same thing here, and substituting for the upper limit, we will have 2 1 cube by 3 minus 1 to the power 4 by 4, and that will give us 2 by 3 minus 1 by 4. 8, taking the LCM, we have 8 minus 3 divided by 12, so which is equal to 5 by 12. So we have evaluated the line integral x squared y dx plus x squared dy, which is equal to 5 by 12. Now let us solve some other problems. Verify Green's theorem in the xy plane for single integral 3x minus 8y squared dx plus 4y minus 6xy dy, where C is the boundary of the region given by x equal to 0, y equal to 0, and the equation of the line which is given by x plus y equal to 1. And the figure goes like this. We have the origin, and A is the point here, and B is the point, and this is the straight line equation x plus y equal to 1. And of course, A will have the coordinates 1, 0, and B will have 0, 1. And this line we have y equal to 0. This line, the line equation for this, y equal to 0, whereas this will be x equal to 0. And we know using this equation x plus y equal to 1, when x is 0, y becomes 1. When x is 1, y becomes 0. So by Green's theorem, we know from Green's theorem, this statement is known, we know already, and this is given in the equation. So comparing this equation with Green's theorem, we have m equals 3x minus 8y squared and n equals 4y minus 6xy. And differentiating with respect to differentiating m with respect to dy partially, we have minus 16y, 0 minus 16y. Differentiating this n with respect to x will have minus 6y. So 0 minus 6y. So we know already using Green's theorem, first we'll start with left hand side. So which is nothing but the total curve mdx plus ndy equal to, look at the figure now, the total curve can be written as O to A to B plus B to O. See, and we have the integrals, line integral O to A first plus A to B, then B to O. So let us solve integral one by one. First we'll go with OA. So we have mdx plus ndy, which is equal to, you have this mdx plus ndy. M is given by 3x minus 8y squared and n is given as 4y minus 6xy. And of course, from the figure, this is O to A. So if O to A, y equal to 0, it implies that dy equal to 0. So dy equal to 0 means this one will, the second term will go off. And in the first term, the second one, y equal to 0, this one also will go off. So we have 3x times dx. So 0 to 1, 3x dx. Integration, on integration will get us x squared by 2. So 3x squared by 2. Substituting the upper limit will give us 1 squared by 2. Lower limiting will give us 0. So 3 multiplied by 1 by 2 is nothing but 3 by 2. So we have obtained now the first integral. We have obtained the value of the first integral. Now we'll go for the second integral. So mdx plus ndy. So here the limits are 1 to 0. So here the limits are 1 to 0. See here. And this goes from A to B. A to B is 1 to 0. See, 1 to 0. Look at the limits, 1 to 0. This is your m and this is your n. And of course, we know the equation x plus y equal to 1. It implies that y equal to 1 minus x. So dy equal to minus dx. Now substituting for the expressions for y, we will have this equation. So we have 3x minus 8. Instead of y squared, you substitute 1 minus x squared dx plus 4. Instead of y, you can substitute 1 minus x minus 6x. Instead of y, you substitute 1 minus x. Instead of dy, you substitute minus dx. Now we expand this alone. So we have minus 8 a minus b whole squared formula. So we have 1 minus 2x plus x squared. Other terms are let it be. So we have now 3x multiplying this expression with minus 8, that will have minus 8 plus 16x minus 8x squared. And here it is minus 4 minus minus plus, so 4x. And here it is minus, one minus is outside, so minus into minus, that will give us plus, so plus 6x. Here one minus is there, another minus is there, and one more minus is here. So we have minus 6x squared. So now minus 8 minus 4 will give us minus 12. 3x plus 16x plus 4x plus 6x, that will give us 29x. And we have minus 8x squared minus 6x squared will give us minus 14x squared. I have written the same thing. Now integrating with respect to x, that will give us minus 12x plus 29x squared by 2 minus 14x cubed by 3. Substituting the upper limit first, we'll have 0. Substituting the lower limit will give us this value. Taking the LCM, we have 6. 72 minus 87 plus 28, which is equal to 13 by 6. So we have obtained the value of the second line integral. Now we'll go for the third line integral. Third line integral is nothing BO. It is not AB. Line integral, this is BO. BO mdx plus ndy, which is given as, this is for m and this is for n. And of course, look at the picture now. This is from B to O. For B to O, x equal to 0. If x equal to 0, dx must be equal to 0. So we have x equal to 0 and dx equal to 0. You substitute here dx equal to 0, this first term will go off. And here x equal to 0, the second term will go off. This alone will exist. So 4y dy. So integration 1 to 0, 4y dy will give us y squared by 2. Substituting the upper limit will give us 0. Substituting the lower limit will give us 1 by 2. So 4 multiplied by minus 1 by 2 will give us minus 2. Now adding all the three line integrals will have 3 by 2 plus 13 by 6 minus 2. Taking the LCM, we will have 10 by 6, which is equal to 5 by 3. So this is exactly, this is for the left hand side. This is for the left hand side. So left hand side we have obtained, we have calculated all the three integrals, we have added, and which is nothing but 5 by 3. Now let us go for the right hand side of Green's theorem. Right hand side is dn by dx minus dm by dy dx dy. And of course we know m and y. So dm by dy partially, that will give us minus 16y. Partial dn by dx is equal to minus 6y. So substituting here, that will give us minus 6y plus 16y will give us, so this will have 10y. So I have pulled 10 out, surface integral y dx dy. Now we have two integrals. And look at the equation, we have x plus y equal to 1. So x equal to y minus 1. Now it's wrong here. X equal to 1 minus y. So there's a mistake here. X plus y equal to 1. We have x equal to y. Instead of y minus 1, we should write 1 minus y. So there's a mistake here. And this limit goes from 0 to 1 minus y dx dy. So we have now 10 integral 0 to 1 y. We have integrated dx, so which gives us x 0 to 1 minus y. Substituting the upper limit will give us 1 minus y. Substitute lower limit will give us 0. So y 1 minus y dy. So which will give us y minus y square dy. So I have written the same thing here. And after the integration will give us y squared by 2 minus y cube by 3. Substituting the upper limit will give us 1 by 2